If you remember, ionic bonding involves a metal like sodium transferring one or more electrons to a non-metal atom like chlorine to form two oppositely charged ions. And these two ions will then be attracted to each other by electrostatic forces, forming an ionic bond. In today's video, take a look at ionic compounds, with a focus on how their structures, all that properties are, and how to draw the 3D structure. In real life though, ionic compounds generally involve tons of ions, not just a couple, like we showed at first, and the positive and negative ions alternate. You can see sodium chloride is a crystal, and in fact many ionic compounds form crystals like this, so in this video we're looking at how the ions are arranged in a crystal, and how this determines the properties of ionic compounds. The first key fact that you need to learn is that ionic compounds form giant structures, and scientists call this a giant ionic lattice. I'm showing you here the giant ionic lattice for sodium chloride. In this lattice we have positive sodium ions, surrounded by negative chloride ions, and you need to remember that giant lattices are three-dimensional structures. In a giant ionic lattice, there are very strong forces of attraction between the positive and negative ions. Ionic bonds act in all directions. Ionic compounds are also very brittle. This means that they break rather easily into small pieces. But why are ionic compounds brittle? When a force is applied to the 3D lattice structure, will disrupt the regular repeating pattern of sodium and chloride ions. So the sodium ions are forced to be next to other sodium ions, and the same is seen with chloride ions. Like charges repel one another, and this repulsion essentially breaks the lattice structure. In summary, ionic compounds exist as giant ionic lattices, not a single molecule. The giant ionic lattice is a regular repeating 3D pattern of alternating positive and negative ions. How to draw sodium chloride crystal structure. Step 1. Draw 3 squares. Step 2. Draw a straight line to connect the square. Step 3. Draw different middle lines. Step 4. Draw the sodium ions. Step 5. Draw the chloride ions. To draw cesium chloride crystal structure, Step 1. Draw 3 squares. Step 2. Draw a straight line to connect the square. Step 3. Draw different middle lines. Step 4. Draw the cesium ion. Step 5. Draw the chloride ions. But we know that there are two key properties ionic compounds that you need to learn. Firstly, ionic compounds have very high melting and boiling point. That's because the strong electrostatic forces of attraction require a great deal of heat energy to break. For example, the melting point of sodium chloride is around 800 degrees Celsius. The second key property of ionic compounds is that they cannot conduct electricity when they're solid. In a solid, the ions are locked in place by the strong electrostatic forces of attraction, so in a solid the ions can vibrate, but they cannot move. But molten ionic compounds can also conduct electricity. The lattice structure is broken at high temperatures, and so the ions become free-floating. Most ionic compounds are soluble in water. For example, sodium chloride, an ionic compound can dissociate into its ions, so when we dissolve sodium chloride, it will dissociate into sodium chloride ions. These ions become stabilized in water, due to the polar nature of water. As you can see, the sodium ions are stabilized by the negative dipole of water, and the chloride ions are stabilized by the positive dipoles of water. This solvation stabilizes the free-floating ions. We can dissolve nickel sulfate in water in a beaker. Please insert 2 rods of graphite into the solution. These will act as electrodes. Using 2 alligator clips, connect 1 graphite rod to one end of the mini light bulb and a LED, and another rod to the other end to complete the circuit. You will see that the LED lights up, hence the solution conducts electricity.